In this next section, which is going to span a couple videos, we're going to look at the change of concentration with time. And to do this, we're going to look at integrated rate laws. And the integrated rate laws relate concentration to reaction time and will show how they can be used to determine the reaction order. So let's take a look at an example reaction, and we'll say this is A giving us B plus C. So we have some sort of decomposition reaction here where we have one reactant giving rise to two products. And if we made a plot of the concentration versus time, we'll see a relationship that looks kind of like this. Again, we have an exponential relationship or a nonlinear relationship. And if we assume that we start with a first order reaction here, we can write the rate of this reaction as a rate law, right? So we talked about writing these as change in concentration over change in time. So if we wanted to express the rate for this, we can say that the change in the concentration of A with respect to time is going to equal K, which is a rate constant, times the concentration of A to the first power. So on the right-hand side, we write out the rate law. On the left-hand side, we write it's the rate of change for this particular reaction. Okay, I'm going to go through some differential calculus here, and I know not all of you have probably had calculus. You'll never be tested on the derivation of this, but I want to kind of shed some light on how we determine each of these relationships and how, you know, we use these formulas. Okay, so if we can rearrange this this particular expression, right? If we take the change in concentration the change in time and put it over here to the right hand side of the equation, and if we took A and exchange it over here onto the left-hand side of the equation and do a little bit of algebra, we get the following expression where we have negative dA over A is equal to K times dt. All right, so if we take the negative sign then and multiply -1 times each side of the equation, this becomes positive and this will be negative. Okay, if we rearrange this to look a little more like what we would do in calculus class, we have 1 over A times d over A equals minus K times dt. And what we want to do now is we want to integrate each side. So if we take the integral from A0 to A of both sides, the integral of 1 over A is going to be the natural log of A. And when we arrange that, we can say the natural log of A minus the natural log of A0 is going to equal negative K times T. And if we rearrange this to see the first order integrated rate law that you see in your textbook, it's going to be the ln of A divided by the ln of A0 is going to equal minus KT. Now we can use properties of natural logs to get rid of this negative sign, because when you typically see an equation represented in a textbook, it's kind of a pet peeve of theirs to include a negative sign. So this is going to be the ln of A0 over A is going to equal KT. And this expression right here is going to be the integrated rate law for a first order reaction. And if we draw this out, okay, we have this initial graph right here where we plotted the concentration of A versus time. Okay, and again, it's nonlinear, but what happens here is if we now plot the natural log of A on the y-axis and time on the x-axis, we're going to get a graph that looks something like this. Okay, and this is linear, which is good because this means we can help predict things a little bit better. Okay, and we're trying to relate concentration and reaction time in the best way that we can. Okay, if we look at this equation, now on the y-axis we have the natural log of A, or the natural log of the concentration of A. On the x-axis we have time. Okay, remember, if we have a y equals mx plus b equation, our slope right here for this particular reaction is going to be equal to k. Okay, so when we look at a first order reaction and we plot the natural log of A versus time, we can get this relationship. And again, I'm not going to ask you to derive this because the derivation of this requires calculus, but we can go through and we can use this integrated rate law expression right here for a first order reaction. Okay? So integrated rate laws enable us to do several things, right? So these integrated rate laws allow us to determine the following. Number one, from this, we can determine the concentration of a reactant remaining at any time after the reaction started. Number two, we can determine the time required for a sample to react. And number three, we can determine the time interval for the concentration to fall a certain level. And we can do this for first order reactions, second order reactions, or zero order reactions. Okay, so this case right here and this integrated rate law that we've derived is for a first order reaction. Okay, we're going to go in and we're going to investigate and derive the integrated rate laws for zero order, first order, and second order. And in the next video, we'll talk about something called half-life and look at the half-life for a first order reaction.